Hello and welcome back. Today we're going to cover indirect proofs. A theorem is of the form P implies Q. And in my last video, part 1, I discussed direct proofs. And direct proof, just to remind you, is you assume P is true and prove Q is true. And that's why this is called direct proof, because you are really using P to get to Q. You assume P is true, do some work, and you prove Q to be true. Now, the indirect proof, or sometimes we refer to them as proof by contradiction or contraposition, based on the following fact. P implies Q is equivalent to not Q implies not P. This is called the contrapositive of this implication. The contrapositive of this implication. So these two are really equivalent. Now, so for instance, if I say, if I live in Ohio, then I live in the United States. So if I live in Ohio, then I live in the United States. Now, if I live in the United States, it's not necessarily that I am living in Ohio. I can be living anywhere else. But if I don't live in the United States, then I don't live in Ohio. See how that's thing. So that's important to remember. That's what we're going to be using in indirect proofs. So instead of proving this, we will be proving this instead. So indirect proof . Okay, sometimes we call it proof by contradiction. By contraposition. So what you do here, you assume so you want to prove Q is true, you assume Q is false. So you assume Q is false. And you prove P is false, or you get a contradiction. So you are proving not Q implies not P. So you want to prove Q is true to begin with. So you say, what if not Q is true, which means Q is false? And then what happens to P and not P? So let's take a few examples to explain this. If n squared is even, then n is even. Okay, so this is P, and this is Q. So again, I recommend that seeing part 1 before continuing to watch this part 2. So we need to prove if n squared is even, n is even. So now you take this and you say, suppose n is odd. Suppose n is odd. So now say, suppose n is odd. And sometimes we say suppose temporarily, suppose for the sake of argument, suppose for the time being, n is odd. Then you can write n is equal to 2k plus 1 gives you n squared equal 2k plus 1 squared equal 4k squared plus 4k plus 1 equals 2k squared plus 2k plus 1 equals 2l plus 1, which is odd. So now n squared is odd, see? And n squared is even, because that's your assumption that we started with n squared is even. See the contradictions? This contradiction happened because we assumed n is odd. Therefore, n must be even. So we proved not q implies not p. That's what we did. Not q. What is q is n even, not q, n is odd. P, n squared is even, not p is n squared is odd. So that's what we did. Take another second example. If 5n plus 6 is odd, then n is odd. So you take this and negate it, okay? So say suppose temporarily for the time being, for the sake of argument, suppose n is even. The opposite of this, the negation of this. So n is equal to 2k, then 5n plus 6 is equal to 2k plus 6, 10k plus 6, 2 outside, 5k plus 3, 2l, which is what? Even. So 5n plus 6 is even, and 5n plus x is odd. Contradiction. And we got this contradiction because we supposed n is even. So n must be odd. Let's take another example. If m times n is even, then m or n must be even. M and n are in integers. So what is my assumption? My assumption is mn is even. That's, I have that. And I need to prove that m or n must be even. So now, proof. Suppose n and m are odds. Because we want to prove one of them is even, at least. So suppose both of them are odd. So n times m will be odd, is odd. And I showed you this in my previous video. You can check it out. It's easy to see. So nm is odd then. So you have nm is odd and even at the same time. Contradiction. You look at it this way, or you say, okay, I proved not Q imply not P, which is proved by contraposition. That's how they're really related. Here's an interesting example. Prove square root of 2 is irrational. So that's really a very typical example for use of by contradiction. So what do you want to prove? You want to prove square root of 2 is irrational. We're going to assume, suppose, square root of 2 is rational. Now I have to get some contradiction somewhere along here, along the way. And when I get this contradiction, I know I got this contradiction because I suppose square root of 2 is rational. So suppose square root of 2 is rational, then square root of 2 is of the form a over b. A, b are integers. And I'm going to assume that it's in its reduced form. In its reduced form. So a and b cannot both be divisible by 2. Otherwise, I reduce the fraction. So this is in its reduced form. So now, if I square both sides, I get 2 equals a square over b square. Then a square is equal to 2b squared, which means a square is even, because 2 times something. Then a is even. We just showed it a little bit earlier. If n squared is even, then n is even. So n is even. Then I can put, sorry, a is even. Then I can put a is equal to, let's put it 2k. So I replace it in here. I have a squared, 4k squared is equal to 2b squared. Then b squared is equal to 2k squared. B squared is equal to 2k divided by 2. So now, b squared is even, because 2 times something. Then b is even. So now b is even and a is even, and that is in contradiction of what we said, that a over b in its simple form. So you see how we got a contradiction, and the reason we got this this contradiction is because we suppose square root of 2 is irrational. So square root of 2 is rational. So therefore, square root of 2 must be irrational. Last question, last example. Show that if n cubed plus 5 is odd, then n is even. Okay, so this is your P, and this is your Q. So suppose the negation of this, suppose n is odd. Now, n cubed plus 5 is n times n times n plus 5. N times n, n is odd. That's what we're assuming here. So n times n will be odd. And see my previous video. Then this is odd, and then you multiply it again by n. That gives you an odd number. Then odd plus 5. Odd plus 5. That's odd. That's odd. That gives you even. So n cubed plus 5 is even. And n cubed plus 5 is odd. And that's a contradiction. Why did we get this contradiction? Because we assumed n to be odd, then n must be even. Also, you look at it as if we proved not Q implies not P, which is proof by contraposition. So to summarize, to prove to summarize, to prove P implies Q, either you say assume P is true and prove Q is true. That's a direct method. Or assume Q is false and prove P is false. So do not, warning, okay, do not assume Q is true, because that's what you're trying to prove. Do not assume Q is true. Do not assume P is false, because P is your assumption that you're starting with as an assumption. It has to be true to begin with. So once you make sure you don't make these mistakes here, then you have only really two options left. Assume P is true, prove Q is true. Assume Q is false, prove P to be a false, which is a contradiction. And that conclude this part. See you later. Thank you very much.